Hello everyone, today we will be starting with a new chapter, that is periodic classification of elements. We will be starting with the session. Meanwhile, you can drop down your names for attendance purpose. You can drop down your names for attendance purpose. Students are requested to drop down your names for attendance purpose. Okay, so we will begin with the session now. First, we will discuss that the chapter name is basically periodic classification of elements, right? And we somehow know that it includes the periodic table, that is grouping of elements. Now, the question arises here that why do we need to form a table, or what led to the basically formation of a table, or why do we need to basically classify the elements, right? What is the need to classify the elements? For example, let us say that at present we are having 18 elements, let us say, right? So you can study and remember each and every element and their properties also, right? Now there is an increase in the elements, let us say 33. Okay, this number is also okay with you, that you can remember the names of the elements and the physical and the chemical properties associated to them, right? Now it comes to 63 elements, 118 elements, so we cannot remember basically the physical and chemical properties of each and every element, right? So if we classify, basically let us say that three types of students are there in the class, right? There are 40 students in a class. There are 40 students in a class, and there are three type of students. First one are the front benchers, which respond to the teacher basically efficiently, right? Next are the back benchers, and next let us say are the middle benchers, right? So if you basically classify these 40 students into the three groups, that is front benchers, back benchers and middle benchers. So you can classify according to their properties, that front benchers are having so and so properties, back benchers are having so and so properties, and middle benchers are having so and so properties. So instead of remembering the properties of the 40 students, now you can group them into the three groups, right? So this is easier way of basically studying the properties of various students. So similarly, if you consider the elements, as there are a lot of elements being discovered, so we do the classification of the elements in groups or in periods basically, right, to understand the relation between their physical and chemical properties, right? So while the evolution of chemistry progressed through discovery of elements, there has been always attempts to understand the similarity in physical and chemical properties, right? So we tend to find out the similarities in the physical and chemical properties of elements, so that as to simplify the study of elements and their compounds basically, because it is impossible to remember the physical and chemical property as well as physical and chemical property of the compounds also separately. Okay. Now early classification, if you say, first was Leviosa, right? So first Leviosa made an attempt to classify basically all the elements. So he classified all the elements by their basic groupings such as gases, metals, non-metals and earths, right? For example, light, heat, inflammable air, he classified as gases. Antimony, silver, arsenic, bismuth, cobalt, copper, tin, iron, manganese, he classified as metals. Sulfur, phosphorus, pure charcoal, he classified as non-metals. Chalk, magnesia, clay, he classified as earths, right? So this was the basis of grouping basically, right? Now here if you see that not all the participants of the group are elements, there are some compounds also, right? If you say clay, it is not an element, it is a compound. If you say chalk, it is not an element, it is a compound, right? While here if you consider antimony, silver, arsenic, bismuth, they are elements. So his classification basically included not all the elements, but also there were compounds also. So around 33 elements were discovered by that time, right? So he classified them as gases, metals, non-metals and earths. Now came the Daubigny triad. So what is triad? Basically group of three. So what he did, he took certain elements basically, right, and grouped them into triads. That means A, B, C are in one triad, D, E, F are in one triad, G, H, I, let us say, these are the elements, these are the third triads basically, right? So A, B, C is forming a one triad, D, E, F is forming another triad, G, H, I is forming another triad. So he said that basically the atomic weight of the middle one, let us say B, is equal to the mean of the first and the third one divided by 2, right? So it is the mean of the atomic weights of first and the third element. I'll repeat again, the atomic weight of the middle element is the arithmetic mean of the atomic weights of the first and the third element, right? So what were the elements which were following the triads? Basically, if you say lithium, sodium, potassium, right? So lithium is having an atomic weight of 7, sodium is having an atomic weight of 23, potassium is having an atomic weight of 39. So if you take the mean of 39 plus 7 divided by 2, it will give out to be 23, which is the atomic weight of sodium basically. Now you consider the next triad, calcium, strontium, barium. So 40 is the atomic weight for calcium, 88 is the atomic weight of strontium and 137 is the atomic weight of barium, right? So if you add up 40 and 137 and divided it by 2, basically if you find out the arithmetic mean of the first and the third element, it is giving out to be 88.5, which is closer to that of the atomic weight of strontium. Next you consider chlorine, bromine, iodine. So chlorine is having 35.5, bromine is having 80, iodine is having 127. So you add up 35.5 and 127 and divide it by 2, that is find out the arithmetic mean of the two. It will give you 81.25, which is approximately equal to 80, that is the atomic weight of bromine. Next you consider sulfur, selenium, tellurium. So add up 32 and 127.6 and divide it by 2, you are getting 79.8, which is closer to that of the 79, that is the atomic weight of selenium, right? So these trades were basically called, these four groupings were basically called triads individually, because they were containing 3 elements, 3 here, 3 here and 3 here. Okay. Now the demerit of Daubigny trades was basically that not all elements are available, not all these elements which are available could be arranged into triads, right? So only grouping of lithium, sodium, potassium, calcium, strontium, barium, chlorine, bromine, iodine, sulfur, selenium, tellurium can be done. Other than these, he was not able to find out the triads basically. Okay. Next came the Newland's octave law, right? So Newland stated that actually he was a musician, right? He was a musician, he loved music. and also he was the chemist, right? So basically he interrelated the two, right? In music we have 7 notes that are known as sa re ga ma pa dha ni sa in Hindi and do re mi fa sol la si do in English, right? So here if you see that he said that the first and the 7th element, right? He arranged the 56 elements known in the increasing order of their atomic weight. This is very important. What he did, that at that time 56 elements were known, let us say. So 56 elements he arranged in the increasing order of their atomic weight. Here you can see that lithium, then beryllium, boron, carbon, nitrogen, oxygen, fluorine. Now neon, argon, they were not known, right? Noble gases were not known till then. Noble gases were not discovered at that time, right? Then sodium, then magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, potassium, right? So he said he arranged these elements in the increasing order of weight, right? Sodium is having more atomic weight than fluorine, then oxygen, nitrogen, carbon, and so on. Now he said that the properties of every 8th element are similar to that of the first one. What does this mean? This means that here if you take, see, as sa and sa are repeated, right? 1, 2, 3, 4, 5, 6, 7 and the 8th is again sa, right? So here also he said that if lithium is 1 basically, so 2, 3, 4, 5, 6, 7. And then the 8th element, that is the sodium, will have the similar properties as that of the lithium, right? Now if you consider, let us say beryllium. For beryllium you will count out 8. 1, 2, 3, 4, 5, 6, 7 and then 8. Magnesium. This means what? That beryllium and magnesium will have similar properties. So every 8th element will be similar to that of the first one. For boron if you will count 1, 2, 3, 4, 5, then 6, then 7, then 8. So boron and aluminium will have the similar properties. So this is how he classified basically the elements on the basis of octave law. Okay. Is it clear? Is it clear to all? Okay. Now what were the demerits of this classification basically, or the limitations? First, inert gases were not discovered till then. This is important, right? So if you see here, now after the discovery of, let us say, neon, it will be lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon and then sodium, right? So 8th element will be now what? 1, 2, 3, 4, 5, 6, 7 and then 8. So this means that lithium and neon should have the similar properties, but it was not found to behave the same way, right? So after the discovery of the inert gases, basically the Newland's octave law failed. Now second one is that beyond calcium this repetition was not observed. So he could classify basically the elements till calcium only using his law. After calcium he was not able to classify the elements. Now this is very important. See, Meyer and Mendeleev were two scientists, Meyer and Mendeleev. So they worked simultaneously, not together, but they were working in the same period of time. However, and they are also having the same, paper. Basically, the topic of the paper is also same. The classification is somewhat similar of the two, as of Meyer also and as of Mendeleev also. But we study Mendeleev because first point is that Mendeleev published his paper soon than that of the Meyer. First point was that, and second was that Mendeleev work was in the form of a table, while Meyer work was in the form of a graph, right? So it is not easy to study a graph basically rather than that of table. Table studying is basically much more easier, right? So therefore Mendeleev got the name for the periodic classification of element. His name got more pronounced than that of the Meyer, right? So we will first study Meyer, Lother Meyer's curve. So what he did, he said that the elements having similar properties are in the same position of the curve. First, he plotted the curve between atomic volume and atomic mass. Volume was taken in centimeter cube and mass was taken in atomic mass unit, that is AMU, which is now known as U, that is unified mass, right? So he plotted the graph of different elements between their atomic volume and atomic mass. Atomic volume on the y-axis, atomic mass on the x-axis. When he plotted the graph, such graph was obtained, right, with certain peaks. He said that the elements having similar properties are in the same position of the curve. For example, here if you see, on the top of the curve is sodium, on the top of the curve is potassium, on the top of the curve is rubidium, on the top of the curve is cesium. So he said that sodium, potassium, rubidium, cesium, as they are holding the same position in the curve, they will be having similar properties, right? Now here if you see, let us say on the descending curve, here you are getting magnesium, here calcium, here strontium, here barium, right? So he said that as magnesium, calcium, strontium and barium holds the same position, therefore they will be having the similar properties, right? And chlorine, if you say it is the ascending curve, let us say chlorine, bromine, iodine. So as their positions are same, therefore their properties will also be same, right? Can you see here that alkali metals, sodium, potassium, rubidium, cesium are at the peaks of the curve. Alkaline earth metals, magnesium, calcium, strontium, barium are at the descending part of the curve. Halogens, if you see, chlorine, bromine, iodine, they are at the ascending part of the curve. So these are having similar properties within themselves, okay? The elements having similar properties are in the same position of the curve. This we have discussed. Most of the transition elements are lying in the broad minimas of the curve. Now here if you see, where are the transition metals? Iron, cobalt, copper, right? And here if you see cadmium, ruthenium, rhodium. So these are all lying at the broad minimas of the curve. So they will be having similar properties, right? So this was the basic curve that was proposed by Lother Meyer. So many other physical properties of the elements also change in a periodic manner, such as atomic volume, density. So here you can say that alkali metals will be not having the same density or atomic volume, but they will be following a general order. That means here let us say that the atomic volume is increasing, right? So this will not happen that there will be a certain decrease, right? So either a trend will be followed, right? Increase or decrease trend will be followed, or they will be having the same or identical property. He proposed that the physical properties of elements are periodic function of their atomic weights. This is very important, right? He said that the physical properties are basically governed by the atomic weights, such as we say that y equals to fx. That means y is dependent on x. Similarly, here also the physical properties depend upon atomic weights. Now do this question. The law of triads is applicable to a group of A, B, C, D. Amongst A, B, C, D, law of triads was applicable to amongst A, B, C, D, law of triads was applicable to anyone with the answer? Okay, Sarayu is saying D. No. Check your answer once. Hydrogen is basically what? Remember the series that was given by Daubinier. Hydrogen is 1, nitrogen is 7, and oxygen is what basically? Sorry, nitrogen is 14 and oxygen is what basically? 16, right? So this will be 1 plus 14, 15 divided by 2, that will be equal to basically 7.5, which is not equal to 16. C. Okay. No, check your answer. Yeah, Ridhishri, you are correct with your answer. It is A. Chlorine, bromine and iodine, right? I'll go to that slide once. See here, lithium, sodium, potassium in one triad, calcium, strontium, barium in one triad, chlorine, bromine, iodine in one triad, sulfur, selenium and tellurium in one triad. So the answer is chlorine, bromine and iodine. So the answer is A. Very good. Next, we will do the Mendeleev's table, right? So after Lother Meyer, basically Mendeleev's periodic table we will study. His full name was Dmitri Mendeleev, basically, right? He made an extensive table of 63 elements, right? And basically this is the original table that was proposed by Mendeleev. This was the original table, right? Which was written in Russian. Basically, right? So the NCRTs are containing that periodic table which are a little bit modified. Yeah, there is a lag actually. No worries, I'll wait for some time after this, okay? So original table was basically in the language of Russian, and the NCRTs, the tables are basically modified, right? They are a little bit modified, they are not the original tables, right? So he made an extensive table of 63 elements, right? Mendeleev's periodic law stated that the physical and chemical properties of elements are the periodic function of their atomic weights, and similar was taken by Mayer's, right? Similar was taken by Mayer's also, that physical and chemical properties of elements are the function of the periodic function of their atomic weights. Now here if you see, this was the table proposed by Mendeleev, right, which consisted of 8 columns and 7 rows. He left places for missing elements in order to have elements with similar properties in same group. So here if you see, he predicted that some element will be there here, right? He left the space for that element which has not been discovered. Actually what happened is that Mendeleev had a dream one night before, and in the dream he saw a periodic table, right? So next day he just wrote down that periodic table on a piece of paper and he performed experiments regarding that, and then he developed the whole idea of this Mendeleev periodic table, right? So what he did, he said that some spaces are left in the periodic table, such as after aluminium one space is left, right? After bromine one space is left, right? So basically why did he left the spaces? He said that these spaces are left because there will be a certain element which will be discovered in the future, right, which will have similar properties as that of the element which would be placed here, right? So he left spaces for the newly discovered elements. Now if you see that after the discovery of noble gases and rare earths are basically the F block elements. We will learn that what are P block elements, S block elements, D block elements, we will learn that, right? Basically the lanthanide series and the actinide series, these are known as the rare earth elements, right? So the Mendeleev periodic table again modified, as there were more discoveries of elements, so he modified the table periodically. Now the table consisted of 9 groups, that is from 0 to 8. 1 group, 2 group, 3 group, 4 group, 5, 6, 7, 8, 9, right? This is the 0 group, first group, second group, third group, fourth group, fifth group, sixth group, seventh group and the 8th group. So in total there are 9 groups, right? Now he said that the 0 group is of the noble gases, helium, neon, argon, krypton, xenon, radon, because they were lately discovered. So he established a separate group of noble gases in which all the noble gases were being kept. This is known as the 0 group, right? Now here if you see, all groups except 0 and 8. So 0 and 8, only one group is there, but the other groups, that is first, second, third, fourth, fifth, sixth and seventh, have been divided into 2 subgroups, A and B, 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 right? So here if you see, in a group, he said that valency remains the same. In a group, valency remains the same, and in a subgroup, properties remains the same. Properties remains the same. That means what? Basically 1A and 1B elements will be having the same valency, right? Hydrogen, lithium, sodium, potassium, copper, rubidium, silver, cesium, gold, francium, they will be having the same valency. But properties can be different. Properties of the 2 subgroups can be different. However, the elements which are placed in a particular subgroup will have same properties. For example, rubidium, cesium, francium will be having similar properties but different that of the copper, silver and gold, right? So within a subgroup, if you see, properties remains the same, and within a particular group, the 2 subgroups will have the same valency. Is it clear? Is it clear? Now here if you see the lanthanide series and the actinide series, if you see the rare earth metal which are known, basically in which the f orbital is filled, right? We have done the SPDF subshell. So where the f subshell is filled or f orbital is filled, they are the lanthanide and the actinide series, right? So here if you see lanthanide and actinide series, they were placed separately because first point that they were discovered lately, and the second point is that they almost all the lanthanide and the actinides were radioactive in nature. All actinides are radioactive in nature, no doubt, but some of the lanthanides are radioactive in nature. So he placed the lanthanide and the actinide series separately. Okay. There is a separate place for the lanthanide series and the actinide series, that is where the F subshells gets start filling. Now here if you see group 8, if you see, it consists of 3 elements, right? Iron, cobalt, nickel, ruthenium, rhodium, palladium, osmium, iridium, platinum, right? So this is consisting of 3 elements. So he said that each long period means what? In which the 8th group is having basically 3 elements, right? So each long period, that means this period and this period, was divided into 2 series. See, as the number of elements were being discovered more and more, what was happening? The table was becoming more complex, right? So he was trying to fit in basically all the elements somehow. So what he did, that each long period he classified as the 2 series, that first 7 elements will be the even series and the last 7 elements will be the odd series. So here if you see, 1, 2, 3, 4, 5, 6, 7 will be the even series and the last one will be the odd series. Similarly for period 5 also and period 6 also. Now we come on to the merits of the Mendeleev's table, right? So basically what is the scope of questions from this introductory part of periodic classification of elements? you can get the merits and the demerits of the various classification. For example, they will ask you that how did Daubigny basically classified the elements and what were the demerits of it, or how Newland classified the elements and what were the merits and the demerits of it. And the most importantly that is asked is the Mendeleev's table, right? So what are the merits and the demerits of the Mendeleev's table? That is important from the examination point of view. Such questions are asked. So lanthanoids or rare earths, right? So these include basically elements from cerium to ruthenium, that is from 58 atomic number to 71 atomic number, right? The word earths refer to the oxides, and in fact elements are found in nature first in the form of their oxides. So here if you see lanthanides, they are found in the earth crust in the form of their oxides. That is why they are called rare earth metals, right? So the name actually sometimes confuses to suggest that their availability may be rare, but that is not so, right? They are called rare earth metal. Why? Because they are found in the earth crust in the form of oxides. Actinides, or they are also known as actinoids, they are from thorium to Lr, that is 103, from atomic number 90 to atomic number 103. This also you have to remember that lanthanide is for 58 to 71 and actinides is from 90 to 103, which are placed separately in the periodic table. Here if you see, this is the lanthanide, this is the actinide. Cerium to ruthenium, 58 to 71, here 90 to 103, right? So here if you see this 58 to 71, here if you see this 85 to 103, so they are placed separately because they are having different properties as that of the same group. Coinage metals were also, he was able to classify, basically he was able to position these coinage metals in his periodic table, that is copper, silver and gold. Because why these are known as basically coinage metals? Because they were once used in the currency. Noble metal, if you see, what are noble metals? Which do not react, or basically they are having very low reactivity. So here if you see silver, gold, platinum, mercury, these are the noble metals. So he was also able to place the noble metals in the periodic table. Transuranium metals. So what are transuranium metals? Elements beyond 92 are known as transuranium metals. So atomic number 92, if you see here, where is atomic number 92? Yeah, this. After this, the elements are known as transuranium metals. Transuranium metals. Okay. Now, the study of properties of elements became more systematic and easier, right? So Mendeleev's table was widely accepted, while the same work was done by Mayer's also, but it was in the graphical form, so it was very difficult to understand the graph basically. Rather, the table was easy. So Mendeleev had the pronounced name than that of the Mayer, right? Also, the second merit was, that is very important, it paved the way for discovery of new elements. This is very important, right? Basically he left spaces for the new elements to be added, right? So here if you see that after boron, he mentioned the missing element as Aka boron, right? So he predicted that it will have an atomic weight of 44, and the modern name, now the element has been discovered, is known as scandium, and it was found to have the exactly characteristic properties as was predicted by Mendeleev, right? So he named it as Eka boron. Why? Because he was having a friend which was writing a book in the Sanskrit language basically, right? So he took the name Eka from that. And it is also known that the friend which was writing a Sanskrit book basically had some picture of the Mendeleev table. Picture means that the idea of the Mendeleev table was also there in the Sanskrit book that was written by his friend, right? So both basically emphasized each other's work. Now here if you see, after aluminium, he named the missing element as Aka aluminium. He predicted that the atomic weight should be 68, and the modern name is now gallium. Aka silicon, after silicon, the element that needs to be discovered, he named the element as Eka silicon. He predicted that the atomic weight will be 72. Now we know that it is germanium. Then after manganese, he predicted the missing element as Eka manganese. He predicted that the atomic weight is 100. So now the modern name, that is after we have discovered that particular element, now the name is technetium, right? Similarly, after tellurium, if you see DVI tellurium, predicted atomic weight 212. So modern name is polonium. DVI cesium, predicted atomic weight was 220. Modern name is francium. Eka tantalum, predicted atomic weight 235. Now it is known as protactinium, right? So these were the missing elements that were previously predicted by, before the discovery even, it was placed, their positions were fixed by Mendeleev in his periodic table. Now the drawbacks of the Mendeleev table, it is very important. First drawback was what? Some of the elements are wrongly placed, though their atomic weights are larger compared to the next one, right? Here if you see argon and potassium, potassium is having a weight of 39, sorry, and argon is having a weight of 40, right? Yet argon was placed before than that of the potassium, right? Similarly, these examples you have to remember. Because he arranged the elements in the increasing order of their atomic weights, but some anomalies were there in his table, that he placed argon before that of the potassium, in spite of argon having more atomic weight than that of the potassium. Similarly, for tellurium and iodine, if you see iodine, it is 126.9 and tellurium it is 127.6, and then also he placed tellurium first and then iodine afterwards. For cobalt and nickel, if you see, cobalt was having 58.9, nickel was having 58.6, yet he placed cobalt first and nickel afterwards. Why did he do so? To match the properties with the group basically, right? Although there is not much difference in their atomic weights, so he just switched on the positions so as to match up their properties. Okay. Now, next was, though the isotopes having different mass. See, what are isotopes? Basically, we have discussed that isotopes are one with the same atomic number, and different mass number, right? For example, if you take hydrogen 1,1, hydrogen 1,2, which is also known as deuterium, tritium 1,3, right? So these are having basically different masses, right? Yet only hydrogen was placed in the periodic table, but not deuterium and tritium, right? They were not having any significant position in the periodic table. And similar with the isotopes of other elements also, such as nitrogen 14, nitrogen 15. Only the position of nitrogen 14 was significant, nitrogen 15 was not given by Mendeleev. Now the next, if you see, subgroup elements do not have sufficient similarity in their properties, yet they are placed in the same group. Now this was very important. I told you that within a group only valency remains the same, however the subgroup do not matches. For example, for group 1, let us say we were having A and B, so the properties of A and B were not matching sufficiently, yet he placed these two subgroups in a particular group. So this was the problem with the Mendeleev's table. The position of hydrogen is uncertain. Now this was very important, right? If you see here, if we see the periodic table basically, yes, see here. Yeah, hydrogen, if you see here, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine. So here if you see, they are generally non-metals, and here if you see, there are generally metals, right? And they are having a valency in group 1, if you see, they are having a valency of +1. So hydrogen can show a valency of +1, but it is a non-metal, right? So he was confused whether to place the hydrogen here in the group 1 or to place the hydrogen here in the non-metals basically, right? So the position of hydrogen was basically not determined, that it should be present in group 1A or basically in 7B, because it was matching the different properties of group 1A and 7B. Ma'am, are we supposed to, what is TAL? Yes, if you want, you can take down notes. I'll wait for a while. I'll wait for a while. You can take down the notes. You can jot down the main points. Not the whole paragraph you have to write, but you can not jot down the main points that I have been discussing. For example, in this slide, you can just write down that 3 examples. Then isotopes having different mass, yet they don't have any different position. Subgroup elements do not have sufficient similarities, and the position of hydrogen is uncertain, right? So you can just jot down small points from each of the slide. Okay, we'll move to the next. Which of the element is not among the missing elements identified by Mendeleev? What should be the answer for this particular question? Which of the elements is not among the missing elements identified by Mendeleev? Candium, polonium, germanium or gold? We have discussed this now only in the previous slide. Which of the element is not among the missing elements identified by Mendeleev? So if you remember, scandium, polonium, germanium were one of the missing elements, but gold was not the missing element because he was able to basically categorize the coinage metals. Yeah, Jainuram, you are correct with your answer. Good. D. Very good. Next, you move on to modern periodic table. Now, this is very important. See here, Mendeleev's periodic table was based on atomic weights, right? He said that the physical and the chemical properties are a function of atomic weights. But now we will study the modern periodic table, which will have a different principle basically, right? So, first comes the Moseley's discovery of atomic number. So Henry Moseley was a physicist basically. He performed an experiment. He took a metal basically and bombarded that particular metal with high speed electrons, right, and he obtained X-rays, right. Now he observed that there existed a systematic mathematical relationship between the wavelength of the X-rays that were being produced when he was particularly bombarding high speed electrons on different metals and the atomic numbers of the elements, right. So this came to be known as the Moseley's law basically, that the root of frequency of the X-rays, we have discussed in the previous session in the atomic structure chapter that X-ray is basically a what? Electromagnetic radiation, right. And we have discussed the characteristic, what is lambda, what is frequency, and also root of frequency of the X-rays that were being produced is directly proportional to the atomic number of the elements, not atomic weight but atomic number of the elements. So this was the basis for the generation of modern periodic table, because the previous periodic table said that the physical and the chemical properties are basically function of the atomic weights, right? And the modern periodic table will have a law basically that physical and chemical properties are a function of atomic number of elements, not atomic weights, but are a function of atomic number of elements. So this is the modern periodic law. It is asked in CBSE sometimes that according to the modern periodic law, what is the basic principle of the modern periodic table? That the physical and chemical properties of the elements are a periodic function of their atomic number, and previously it was taken as atomic weight. So after Moseley's experiment, we said that physical and chemical properties are a periodic function of the atomic number. What is atomic number? What is atomic number? Write down the definitions we have done in atomic structure chapter. What is atomic number? What is the definition for atomic number? Anyone? Number of electrons or number of protons? Very good. So atomic number is basically number of protons, which in turn is equal to number of electrons in a neutral atom. Right? Good. So, yeah, Januram, you are also correct. Number of protons in an atom. So this is the modern periodic table if you consider, right? So this is there are no subgroups if you see 1A, 2A, 3B, 4B, 5B, 6B, 7B, 8B, 1B, 2B, 3rd. So there is basically a rearrangement. First, if you see the old periodic table, here it was what? 1A and then simultaneously 1B. Then it was second A and then simultaneously second B. But here the positions have been rearranged. Right. So here if you see 1A, then second A, then third B, fourth B, fifth B, sixth B, seventh B, eighth B. Then if you see here 1A and 1B are separated, right? They are not placed in within a particular group. They are separated now. Similarly, second A and second B, third B and third A, right? So this was the classification based upon the increasing atomic number and not increasing atomic weight. This was based on increasing atomic number, that is increasing the number of protons, right? So here if you consider how many groups are there, 18 groups are there, 18 groups. And how many periods are there? 1, 2, 3, 4, 5, 6, 7. 7 periods are there. And the F block, that is the lanthanide and the actinide series, the part of the radioactive elements in which the F block gets start filling, is placed differently, right? Is placed differently from that of the modern periodic table, like it was placed in the old periodic table. In the modern periodic table also, lanthanides and actinides are given a separate place. Okay. So you can note down this, that there are 18 groups and 7 periods in which lanthanides and actinides have a separate position. No, these are only the names of the subgroups A and B, because they were arranged according to the increasing atomic number now, right? So here if you see in the previous table, see here in the previous table, if you will see, they are arranged in the pattern of increasing atomic weight. Now when you arrange them in the order of increasing atomic number, so their places would be shift now. And also that was the drawback of the old Mendeleev table that the subgroups did not have matching properties, right? So he separately placed the subgroups differently, because the two subgroups were, when placed in a singular group, were the properties of the elements were not matching. Got it? If you take, let us say, 1A and 1B, so that was the problem with the previous Mendeleev table, that the elements of the subgroups were not matching with each other, right? So it was better to place them separately. The modern periodic table does not consist of these two subgroups placed in a single group. Okay. Now see here, the first two groups are known as S block elements. The first two groups 1 and 2 are known as the S block elements. From group number 13 to group number 18 are known as P block elements. The transition between S and P is basically D block elements. So from group 3 to group 12 there are D block elements, which are also known as transition metals. Right? And here are the F block elements, that is the lanthanides and the actinides. Okay. Now we will study separately the different groups and their elements. So why group 1 and 2 are known as S block elements? Because in them the last electron enters into the S orbital. So the elements in which the last electron is entering the S orbital, for example, let us say hydrogen, it is 1s1, right? If you say lithium, let us say, it is 2s1. Sodium, if you see, the last electron entering the S orbital, 3s1. So all the elements in which the last electron is basically entering the S orbital are known as S block elements, right? So here if you see group 1 and group 2, group 1 are known as alkali metals, write it down, group 1 are known as alkali metals and group 2 are known as alkaline earth metals. Group 1 are known as alkali metals and group 2 are known as alkaline earth metals. We will come on to the electronic configuration. So this is the mnemonic for group 1. For group 1, that is hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. So you can remember it as highly naive kids rub cat's fur. Highly naive kids rub cat's fur. So H stands for hydrogen, Li stands for lithium, Na stands for sodium, K stands for potassium, rub stands for rubidium, cat stands for cesium and fur stands for francium. This is group 1. This is group 1. Okay. So if you write down the electronic configuration of hydrogen, lithium, sodium, potassium, rubidium, cesium and francium, now you don't have to remember the electronic configuration, you can do it group wise only, right? So hydrogen, let us skip hydrogen because it is having a separate place. Let us take lithium first, right? So lithium is basically what? 2s1. So sodium will have a outer electronic configuration till 3s1. Potassium will be 4s1. You can see that the outer electronic configuration is remaining same, only the shell number is increasing. 2, 3, 4, then this will be 5s1, then this will be 6s1, then this will be 7s1. So this is how you can remember the outer shell configuration of a particular group. Now next write down group 2. Group 2, beryllium, magnesium, calcium, strontium, barium, radium. Veena and Meghna came straight back rapidly. Veena, Meghna came straight back rapidly. Beryllium, magnesium, calcium, strontium, barium, radium. If you write down the electronic configuration, what is the atomic number of beryllium? Hydrogen, helium, lithium, beryllium. That means 4 electrons. So it will have electronic configuration of 1s2, 2s2. So the outer shell electronic configuration is 2s2. This will become 3s2. This will become 4s2. This will become 5s2. This will become 6s2. This will become 7s2. So the general electronic configuration of group 2 is ns2 and group 1 it is ns1. ns1. This is the outer shell electronic configuration. Written? Shall I move to the next slide? Shall I move to the next slide now? Done with the writing part? See here, because last electron is entering the S in both the cases, in group 1 also and in group 2 also. Therefore, they are known as S block elements. Good. Now, next we will write down P block elements. So, in elements where the last electron is entering the P subshell, that are known as P block elements. So, from group 13 to group 18 are the P block elements. Are the P block elements. See, for S block, if you see, what will be the number of valence electron? That will be, for group 1 it will be 1, right, and group 2 it will be 2. Can you see that? Because 2 electrons are in the outermost shell, so valence electron will be 2 for group 2 and valence electron will be 1 for group 1. Now, if you consider for P block it is equal to number of electron present in the S and P orbital having highest principal quantum number. This is very important. Now, see here. For boron, if you see, the atomic number is 5. The electronic configuration will be 1s2, 2s2, 2p1. For carbon, if you take, it will be 1s2, 2s2, 2p2. For nitrogen, if you take 1s2, 2s2, 2p3. So, now if you want to find out basically what are the valence number of electrons, that will be equal to S plus P, that is 3 electrons, because it is having the same principal quantum number. The shell is same, right? However, the subshells are different. The S and P are different, but the shell is same. And we count the number of electrons by the shell method basically, right? So, it will be 2 plus 1. 2 plus 2 for carbon, that will be equal to 4 valence electron. 2 plus 3, that will be equal to 5 valence electron, and so on. So, for P block elements, you have to calculate the number of electron in S and the number of electron in P subshell having highest principal quantum number. This is very important. The total number of valence shell electron is equal to its group number, that we will see in the next slides. Now, see here, this is for elements of group 13 that are known as boron family. Elements of group 13 that are known as boron family. So you can remember the mnemonic as Baggett. Baggett, that is boron, aluminium, gallium, indium, thallium. Baggett, B-A-G-I-T, Baggett. Boron, aluminium, gallium, indium, thallium. Now write down the electronic configuration for group 13. It will be what? 1s2, 2s2, 2p1. So aluminium will have 3s2, 3p1. Gallium will have 4s2, 4p1. Can you see that the number of valence electron and the general electronic configuration is remaining the same, but the shell number is changing here. 5s2, 5p1, then 6s2, 6p1. So now you don't have to write down basically the whole electronic configuration for a particular element. You just have to learn that in which group does that particular element belong, and then you can write down the electronic configuration as such, right? So the general electronic configuration for boron family will be Ns2 Np1, Ns2 Np1. Now group 14, it is known as the carbon family. Carbon family, because the first member is carbon. Yes, all of them will be having 1s2. See, actually this is the outer configuration. If you write down the, for aluminium it will be 1s2, 2s2, 2p6, 3s2 and then 3p1. I am just writing down the outer shell electronic configuration, right? For gallium also it will be like this only: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1, right? So this whole you have to write down if someone is asking you the full electronic configuration. But valence shell, you can just write down this. You can mention if you want. This I am writing down only the outer electronic configuration, that it will be filled basically up to 5s to 5p1 or 6s to 6p1 or 4s to 4p1 or 3s to 3p1. You have to start it from 1s2. Okay. Now write down group 14. Group 14. Write it down first, I'll rub it. Group 14, that is the carbon family. So this will be carbon, silicon, germanium, tin, lead. Carbon, silicon, germanium, tin, lead. Mnemonic is cute sisters get small, or you can remember it as tiny problems. Cute sisters get small problems, or cute sister get tiny problems. From tiny you can remember tin. Write down the electronic configuration. This will be 1s2, 2s2, 2p2. Then this will be from 1s2 to 3s2, 3p2. Then it will be from 1s2 to 4s2, 4p2. Then tin will be from 1s2 to 5s2, 5p2. Then lead will be from 1s2 to 6s2, 6p2. So the general configuration is Ns2, Np2. Ns2, Np2. Each having the valence electron as 4, because we have to count down only the highest principal quantum number. So here if you see, the highest principal quantum number is 2. So count 2 electrons of S, 2 electron of P. Here the highest principal quantum number is 3. So count S also, P also, 4. This will also have 4. This will also have 4. This will also have 4. So the number of valence electrons in carbon family is 4. We shall move to next. Next is group 15 elements, that is also known as nicogens. They are also known as nicogens or nitrogen family. Nitrogen family. You can remember this as nitrogen, phosphorus, arsenic, antimony, bismuth. Mnemonic for this is: new police assigns subordinate Bikram on duty. New police assigns subordinate Bikram on duty. So this becomes, if we write down the electronic configuration, one S2, 2S2, 2P3. This will be equal to basically from 1S2 to 3S2, 3P3. This will be from 1S2 to 4S2, 4P3. Antimony will be 1S2 to 5S2, 5P3. Bismuth will be from 1S2 to 6S2, 6P3. So the general electronic configuration of the nitrogen family is NS2, NP3. The outer shell configuration, NS2, NP3. Elements of group 16, they are known as chalcogens. They are known as chalcogens, right? So oxygen, sulfur, selenium, tellurium, polonium. Oxygen, sulfur, selenium, tellurium, polonium. Mnemonic for this is: O Seema sent the post. O Seema sent the post. Write down the electronic configuration. This will be from 1s2 to 2s2, 2p4. Then sulfur will be from 1s2 to 3s2, 3p4. Selenium 4s2, 4p4. Tellurium 5s2, 5p4. Polonium from 1s2 to 6s2, 6p4. So the general electronic configuration becomes ns2, np4. That means the total number of valence electron will be how much? Equal to 6 for this family. 6 for this family. That is known as the oxygen family. Oxygen family. Group 17, they are known as halogens. So fluorine, chlorine, bromine, iodine and astatine. Fluorine, chlorine, bromine, iodine, astatine. You can remember this as first class biryani in Austria. First class biryani in Austria. These family are known as halogen family. Halogen family. If you write down the electronic configuration, basically this will be equal to fluorine, chlorine, bromine, iodine, astatine. For fluorine it is 1s2, 2s2, 2p5. So chlorine will be from 1s2 to 3s2, 3p5. Bromine will be from 1s2 to 4s2, 4p5. Iodine will be from 1s2 to 5s2, 5p5. For astatine it will be from 1s2 to 6s2, 6p5. So the general electronic configuration of group 17 is ns2 np5 having 7 valence electrons. 7 valence electrons. That means 7 electrons in the valence shell. 7 electrons in the valence shell. A few more minutes I'll take, just 2 to 3 minutes, and then we'll complete the modern periodic table. Then we will end up the session. Okay. I'll just take few more minutes. Next, write down group 18 that are called noble gases. Noble gases. So this becomes helium, neon, argon, krypton, xenon, radon. So this becomes hero never arrived, hero never arrived, Kiran, Kiran, KR you can remember it as Kiran, Xeroxed, xenon you can remember it as Xeroxed from Rohan, Rohan, radon you can remember it as Rohan. Hero never arrived. So what did Kiran did? He Xeroxed from Rohan because his hero never arrived. Okay. So jokes apart, let us write down the electronic configuration of these. Now this has an anomaly here. If you see, it is 1s2. Here if you see, it is 1s2, 2s2, 2p6, right? So except helium, all will have the same general electronic configuration except helium because it is having only 2 electrons. So it is occupying only one shell. The electrons are occupying only the K shell. Argon if you see, it will be from 1s2 to 3s2, 3p6. Krypton it will be from 1s2 to 4s2, 4p6. Xenon if you will see, it is 1s2 to 5s2, 5p6. Then radon if you see, it will be from 1s2 to 6s2, 6p6. So the number of valence electron is 8 because their octet is complete. Basically that you will learn in chemical bonding also, that why these gases are called noble gases, because they are unreactive. They are having full 8 electrons in their outermost shell. So they are stable in themselves. They do not want to gain electron or to lose electron because exactly the same number of electrons are present which are required for the stability. Okay, that is why they are called noble gases or inert gases or inert gases. Now here if you see D block elements and F block elements you will study in higher classes. Basically in 12th class you will study about the D block elements, and then there you can remember the mnemonics for the D and F block elements. There is no need in the 11th class basically, right? So only in 11th class S and P block are important, and in 12th class you will learn about the D block elements and the F block elements, right? So this is very important. See, the outermost shell is known as valence shell. The outermost shell is known as valence shell. The shell next inside to the valence shell is known as the penultimate shell. Penultimate shell. and the shell inside the penultimate shell is known as the anti-penultimate shell. Anti-penultimate shell. So the outer one will be called valence shell, inside it will be the penultimate shell, and inside the penultimate shell it will be the anti-penultimate shell. Okay, so if the last electron is basically entering into the d orbital, the elements are known as d block elements. The elements are known as d block elements. So they have a general configuration of ns and n-1 d orbital. Ns and n-1 d orbital. For example, cobalt you write down, right? Cobalt is having an atomic number of 27. If you write down the configuration, it will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7, correct? 2, 4, 10, 12, 18, 20, 27, yeah, right? So now counting the number of electrons that are present in basically the valence shell, that will be this ns plus n-1d, that is when n is 4, basically this will be 2 electrons and n-1 will be 3. So this you also have to count out. So the valence shell electron counting for d block elements is basically ns plus n-1d. So here if you see 2 electrons plus 7 electrons, right? So 9 electrons. Similarly, you can take it for iron also. It is 4s2, 3d6, the outer electronic configuration. So the number of valence electron will be 2 plus 6, that will be equal to how much? 8. However, all the electrons are not lost in case of cobalt and iron. If you see, all the electrons are not lost. In case of ruthenium and osmium, you can find out that all the valence electron shell are being lost. That we will deal in the d block elements. No need to basically discuss it here. You can just remember that what is basically the d block elements general electronic configuration. Next we will move on to f block elements. So the general valence shell electron configuration is, just you can remember the formula: ns2, n-1, d0 to 1 and n-2, f1 to 14. This you will do in elaboration when we will do the f block basically in the 12th class, right? For the time being, you can just write the formula. Yeah, so I think that's all for today. In the next class, we will do the basically the nomenclature of the higher elements. Okay. Yeah. So you are requested to kindly watch out the videos, and then we will have basically the work session, right? The recorded videos will be uploaded on the Conceptory YouTube channel. Watch it, the videos from there, and then we will perform the JEE mains work session and the JEE advanced work session on Tuesday, I guess, right? Rest will be informed to you by the coordinator itself. So that's all for today. Thank you. Happy learning to all.